Hello. In this video, we're going to talk about negative feedback and how it affects the frequency response of an amplifier. We have talked about already how negative feedback affects parameters such as the gain of the amplifier, basically decreases the gain by an amount that is proportional to the amount of feedback, which is related to the loop gain of the system. We have also seen that it increases input resistance, or rather increases or decreases input resistance and output resistance by the same amount, the amount of feedback, depending on the type of feedback configuration that we have. And so we have seen that negative feedback has all these great benefits at the expense of gain. And so our generic design strategy for our voltage amplifiers, in this case, is going to be the following. So our design strategy or in our case, we're designing mostly voltage amplifiers, is going to be, one, we're going to design with a very large open loop gain, and we have seen that we're able to achieve that using something called active loads. And so design system with large open loop gain. I'm going to express that as the open loop gain goes to infinity, because we're not concerned about a specific value of the gain any longer. We're going to see that we're going to be able to control that with the negative feedback. The gain is going to become practically independent of the open loop gain. But again, all our calculations, the approximations are only valid if the open loop gain is very large. That's the only circumstance under which we can approximate the closed loop gain of the system to the 1 over the feedback gain, 1 over the feedback factor. And so we're going to design with large open loop gain, and that's basically for lower sensitivity to variations in process parameters, for increased linearity, lower sensitivity to noise, better input and output resistance. And then we're going to use negative feedback to stabilize the gain. And again, if we've designed the system correctly, our closed loop gain, which I'm going to refer to as A sub f, gain of the feedback system, is going to be approximately equal to 1 over beta, or mostly independent of the open loop gain. And again, this is to give us lower sensitivity to process variations, noise, increased linearity, what else? Better, improved I-out characteristics, input-output characteristics, and by that I just mean input resistance and output resistance mainly, etc. At the expense of overall gain for the system, because as we have seen, negative feedback decreases the overall gain of the system by a factor of 1 plus A times beta. So negative feedback decreases gain by a factor of 1 plus A times beta, meaning the gain of the feedback system is going to be equal to the open loop gain divided by the amount of feedback, 1 plus A times beta. What we have not seen is what effect does negative feedback have on the frequency response of the amplifier. And as we're going to see, it does have an effect which it can be potentially detrimental to our amplifier. And you can solve this mathematically just by putting out a generic expression for for the gain based on a rational function where you can differentiate different poles and so forth. But essentially what it's going to do is negative feedback is going to increase the bandwidth of your amplifier by an amount which is also 1 plus A times beta, the amount of feedback. And so we are decreasing the gain, but increasing the bandwidth by the same amount. So negative feedback increases bandwidth by the same amount, 1 plus A times beta. Therefore, the bandwidth of my amplifier with feedback is going to be equal to the bandwidth times 1 plus the loop gain A times beta. Therefore, because we can see that negative feedback decreases the gain but increases the bandwidth by the same amount, we say there is a trade-off between gain and bandwidth in a negative feedback system. So there is a trade-off between gain and bandwidth in a negative feedback system. And because the gain is increased by the same amount or decreased by the same amount that the bandwidth is increased, thus we conclude that the product of the gain times the bandwidth must be a constant. We can solve that over here just with the two expressions that we have written. We can rewrite that as AF gain of the feedback system times bandwidth of the feedback system is equal to open loop gain divided by amount of feedback times open loop bandwidth times amount of feedback. We can cancel those two expressions out, and we're left with the fact that this is equal to the open loop gain times the open loop bandwidth. Because the product of gain times bandwidth remains constant, it receives a special name. It becomes a figure of merit. And it's typically referred to as the gain bandwidth product. So not something very original, but gain bandwidth product, which is equal to the product of the gain times the bandwidth, both for the open loop as well as the closed loop system. And that's also equal to the unity gain frequency, often referred to as the transition frequency. That's why the name F sub t. And that's typically the parameter that comes tabulated in the datasheet. You will either find the GBP, gain bandwidth product, or FT, the unity gain frequency. It simply is the frequency at which the gain of the amplifier becomes 1 or unity. And you can see that, 1 times FT, FT will be the bandwidth of the unity gain system, and therefore it's equal to the gain bandwidth product. So I'm going to write there, this is the gain bandwidth product, and this is the unity gain frequency, or transition frequency. Now, you may ask, well, why does the gain become 1 at some point? And if you recall, for any amplifier, we're going to have limited bandwidth, and on the high end of the frequency, that low pass filter response that we had was due to the internal capacitances of the transistor, as well as parasitic capacitances, load capacitances, etc. But the typical response for any op-amp system, the frequency response, and for now I'm just going to focus on the magnitude response. So basically, if I were to plot, make a plot of my magnitude versus frequency, magnitude in dBs, I will have my open loop gain for the system in dBs, which would essentially, let me do it in a different color. Maybe orange, or let's do blue for the open loop one. Basically, I will have that my gain remains constant within the bandwidth of the amplifier, and then at some point there is a pole and my gain falls off at the rate of negative 20 dBs per decade if we are talking about a single pole system. And then at some point that gain of the amplifier, that magnitude response, is going to reach unity or 0 dBs. That frequency is what's termed the FT frequency. I'll put that in black just because that's my transition frequency. And basically, when I am applying negative feedback, what I'm essentially doing to my magnitude response is I'm decreasing my gain in the pass band, in the midband of region of the amplifier, but I'm extending my bandwidth. So in essence, what I'm doing is I'm shifting my pole, right, from a lower frequency to a higher frequency, so that my gain is lower. And then for frequencies beyond that, it's pretty much the same slope. So this will be the location of my pole with feedback, and the original X here will be the location of my pole without feedback. So in essence, what we have done with negative feedback, we have shifted the location of the pole. And so we have reduced the gain, but we have increased the bandwidth. This will be, of course, the magnitude of the gain for the feedback system in dBs. Maybe I'll put this one in blue, so you can see the relationship there. If you wanted to see what's happening just for a graphical tool in the S-plane, right, the complex frequency plane, where you can do your root locus analysis. So if this is my S-plane, this will be my real axis, this will be my imaginary axis, and I can have, in this case, I have a single pole. It's got to be a real pole because imaginary poles come in complex conjugate pairs. And so in essence, I will have a real pole, and initially it was located at a certain frequency. And I'll represent that with blue, so that we can relate it to the original graph. So we will have a pole at a certain frequency, Fp, and essentially what we have done is shifted that pole to the left, because in order to have a stable system, my poles need to be to the left of the imaginary axis, and this will be my pole with feedback. So in essence, this is the value of my pole with feedback. This was the value of my pole originally. So that's all we've done with our negative feedback. Now we can see that in a single pole system, whenever we have a pole, we're going to introduce as well a phase shift. So not just the magnitude gets changed as we go through the pole, the value of our magnitude changes, but also we introduce phase shifts with every pole that we introduce in our system. For a single pole, there is a maximum phase shift of 90 degrees. For a two-pole system, there's a maximum phase shift of 180 degrees, etc. And that's going to be obviously for the range of frequencies that are above that cutoff frequency. So let me kind of write the equation here. Imagine that we have our feedback system as a function of frequency. Again, it's just going to be the ratio of V out over Vs, and we have seen that it is equal to the open loop gain divided by the amount of feedback. So this will be a function of frequency divided by 1 plus, in the most generic case, both the feed-forward gain as well as the feedback factor are going to be functions of frequency. What we have done in this case, the location of the pole with feedback is going to be equal to the location of the pole without feedback, the open loop, location of the pole times 1 plus A times beta. So in essence, that's what we have done. Now, something to note is that at some point, as I was mentioning earlier, at some point, if I introduce two poles, my maximum amount of phase shift for a certain range of frequencies is going to be 180 degrees. And when I have negative feedback with a phase shift of 180 degrees, I run into the problem that negative feedback can become positive feedback. How does that work? Let's make a little note here. Let's imagine that you have your op-amp. Your amplifier with a gain A. I'm going to refer to the op-amp because it's a system that you know, and you're probably it's probably easier to visualize than just an abstract block diagram. Let's imagine I have a feedback network. This could be simply a non-inverting amplifier where my signal is applied at the non-inverting input terminal, and my feedback network is just those two resistors. Right? This will be my output signal, which I sample, run through my feedback network, and feedback to the input of my amplifier. And let's imagine for a certain range of frequencies, I'm going to have a phase shift that is lower than 180 degrees, and so there is no problem. Let's imagine I have my signal. First, I'm going to do it with blue. I have my input signal. Because this is a non-inverting amplifier, this is going to go to my output. It's going to produce an output signal in phase with the input signal. That output is going to be sampled, run through the feedback network. Typically, the feedback network is going to have the feedback factor is going to be something less than 1. In the case of the non-inverting amplifier, you have a voltage divider, so it's going to be something less than 1. That's going to get multiplied times the output signal, and I'm going to get a signal at my negative input. If my op-amp is operating properly, it's going to be of the same, perhaps not very clear in this image, but it's going to be of the same magnitude as my positive input terminal signal. And so when both of them get subtracted from each other, my error signal, which is what I feed into the input of my op-amp, is going to be approximately equal to 0. Now, let's imagine for a second that I'm running my signal at a frequency for which I am past the two poles, and so I have a phase shift of 180 degrees. So if my output signal is shifted by 180 degrees now, it will look something like this. Basically out of phase with my input signal, and therefore that's what's going to get fed to the negative input terminal of my op-amp. Now when I subtract my positive signal minus this signal which is out of phase, so it's basically opposite, I'm going to get, minus minus is equivalent to adding the two signals together or having twice my input signal. And so I can see that my signal, in going through the loop, sampling the output and coming back, my input signal has essentially doubled. And then it's going to run through the loop again, and if the same thing happens, it's going to keep increasing. And the idea is that I'm going to have an ever-increasing oscillation in my signal. In practical terms, the power supplies of the op-amp are going to limit, so my oscillation is not going to keep growing towards infinity. That will just be mathematically. Because the op-amp has limited supplies, it's just going to be trending towards the rails of the op-amp, and then you're just going to have basically an oscillation that goes from positive to negative rail. But that's how negative feedback has become essentially positive feedback, is because I have introduced a phase shift of 180 degrees And so something that should have been a negative signal has now been inverted. Okay. If we wanted to represent it in the more generic block diagram for a negative feedback system, I will have the following. I will have my amplifier. I have my source signal that's fed to the amplifier. The output signal comes out, X out. It gets sampled, run through a feedback network, multiply times the feedback factor beta, and then fed back in a way that it, X sub f, the feedback signal, gets subtracted from the source signal to give me the error signal, X sub I. Now, if I have a phase shift of my original source signal throughout the system of 180 degrees, that's equivalent to multiplying my signal times -1. It's basically taking the inversion of my signal. And so my a 180 degrees phase shift is equivalent to multiplication times -1 by a factor of -1. And so therefore I will have, my xf prime will be equal to negative xf. And so negative with negative, basically my feedback signal will be adding my source signal, and therefore my error signal will be larger than the source signal as opposed to smaller than the source signal. And so that's how the 180 degrees phase shift has transformed negative feedback into positive feedback. So the main idea to keep in mind is basically that negative feedback not only affects the magnitude response of a system, but also the phase response of a system. In the magnitude response, we have seen that it decreases the gain and it shifts the cutoff frequency, therefore shifting the bandwidth of the amplifier. But negative feedback also affects the phase response of a system. And basically a phase shift of 180 degrees can turn negative feedback into positive feedback. Why is this important? Well, we have seen that positive feedback can introduce all sorts of undesirable effects, such as oscillations, and therefore we want to watch out when we design a voltage amplifier and we apply negative feedback. We want to watch out that it is still a voltage amplifier and not an oscillator. So we're going to next take a look at how we analyze the stability of a system, of a negative feedback system, and then later on, for systems that are unstable, we're going to analyze techniques to make them stable.